Alright everyone, before starting the video I would like to request all of you to join the Discord server given in the description below. If you can discuss our doubts or even interact live. And, well, make sure you subscribe to the channel and like the video. Let's jump into it. Alright guys, today we are going to discuss some questions for electrostatics. So basically the level is going to go from basic to advanced. I'll be releasing 4 parts of this video, and in each part we'll do 10 questions, and the difficulty is only going to go up, and these questions will be very highly relevant to JEE Advanced and they'll help you summarize the whole chapter with these questions. If you practice these, I'm sure you won't need any other questions to be practiced. Well, let's get started. The first question says a ring with uniform charge distribution with a total charge Q and radius R is placed in the YZ plane with its center at origin. Okay, so let us draw the YZ plane, and this is 0, 0 and 0, and with respect to it is x-axis. Now, which of the following statements is or are correct about this situation? So the field at origin is going to be 0. Yes, that is true because the center is at origin. So I think we can just mark this off. The potential at origin is going to be kq by r. Yes, it is also true because by symmetry we know that all these infinitesimally small point charges are at a distance r. So when we integrate k dq by r, we get kq by r. This is how we remember this result. Now we have to find the field at x 0, 0, where x generally means a point on x-axis. So the way I would like you to do that is, I would like you to visualize a ring and then passing through its center is an axis perpendicular to this and this, right? They are mutually perpendicular axes. So what's basically happening here is we have to consider this in this case, right? This distance. Now this distance is going to be r square by x square. Now the field at this point can be given by the expression kq by distance. So the distance squared. Now the distance can be given by this expression, hence this would satisfy. Let's move on to the next question then. Two concentric shells have radii r and 2r. Charges qa and qb have potentials 2v and 3 by 2v respectively. Now shell B is earthed by closing the switch S. Let the charges on shells change to qa prime and qb prime. Then we have, okay, so first we need to figure out the ratio of initial charges. Okay, so we have been given the potentials, right? So what we can do is we can basically kq1 by r is the potential on this surface due to the charges present on this surface itself, right? Then the potential on it due to the other shell, the other surface, is going to be kq2 by 2r. When you add them, you are getting 2 volts. Is that what's, yeah, I think. All right. Then in the second case, what's happening is kq1 by 2r plus kq2 by 2r is given by the expression 3 by 2v. So basically what's happening is you can just subtract these equations and you will get that kq by 2r, kq1 by 2r is equals to 1 by 2v, and we cancel out the 2 and we get kq1 upon r equals to 1 volt. Then we can just put it into this equation and we get the value of this. This is also going to be 1 volt, and we just double it to get the value of Q2 by R, right? Then we can get the ratios of 1V and 2V, which does satisfy this equation. So basically in the second part, what we are going to do is we'll first rub both the shells. We know the second shell is grounded. That means the potential at it is equals to 0. Now the expression of VB can be written as QA dash upon 2R plus Q KQB dash upon 2R. This is how we write it. Now this has to be equal to 0, and we already know that QA prime is equal to QA because it is not being earthened. So this is not going to change. The charge on this one is not going to change, right? So what essentially happens is QA prime is equals to negative of QB prime. So this is incorrect, but had it been the modulus of both of them, it would have been correct. Now let's solve for the second part. The potential of VA becomes what? So the potential due to QA prime upon R would be 1 volt, and then you have 0.5 volts but in negative because of QB prime. So it is not going to be this. This is incorrect again. It's going to be somewhat like this. The potential difference between A and B after earthing. The option is not there, so we can just calculate what the potential difference is going to be. So the potential difference is going to be this minus 0 volts, because it is essentially the potentials of both of them subtracted from each other. So yeah, we can just write the answer as 1 upon 2 volts. Now let's solve for the third question. Which of the following statements is or are correct? If the electric field due to a point charge varies as 2 raised to the power negative 2.5 instead of 2, then the Gauss law will still be valid. So this is a very ambiguous question. Gauss law basically is derived from Gauss diversion theorem, which will be valid for this in a 4D space and so on. But we are not being provided any information regarding the subspace or regarding the changes in Coulomb's law or anything like that. So what's essentially going to happen is we'll not mark it correct because it is too ambiguous to be marked correct. Now let's move on to the second option. The Gauss law can be used to calculate the field distribution around an electric dipoles. So yes, I think we can use it to, okay, no. Gauss law cannot be used to calculate a non-uniform and non-symmetric field distribution around an electric dipole. So yeah, again, it is very ambiguous. So I'm not sure if we can mark it correct, right? Because we have not been provided what we are essentially trying to. We have not been provided a specific case, and it cannot work for non-uniform distributions, which are non-symmetric as well. So yes, we are going to mark it incorrect. Now moving on to the third option. If electric field between 2 point charges is 0 somewhere, okay, let's assume it Q1, let's assume it Q2. The electric field somewhere between them is 0. F net is equals to 0. That means they are of same sign, because only then is it possible that they are trying to accelerate it in opposite sides. So yes, this is correct. The work done by external force in moving in unit positive charge from point A potentially to, okay, yes, this is correct. This is just the definition of work done, and Potential difference, essentially. Potential difference is the work done in moving a net positive charge from one place to another. So yes, that's it. Now let's move on to the fourth question. A few electric field lines of the system of two charges Q1 and Q2 fixed at two different points on the x-axis are shown in the figure 1.422. With the figure, what information about charges and electric field we are getting? So first of all, we are getting that these field lines are denser than these field lines, or we can also say that there are more field lines in total than these field lines. So Q1 is going to be greater in magnitude. Now we need to see which of these two options is going to be correct. At a finite distance to the left of Q1, the electric field is 0. So essentially what finite means is it is relative to infinite, right? What it essentially means is that one of them will have their field extinguished a lot farther away than the other one, right? The influence of their field will get extinguished in varying extents. So the finite distance, this term essentially means which one's field will get extinguished first. That's what it means. So yeah, we can analyze that this is going to be the case with Q2 because it is less dense and it is less in magnitude. And yeah, that's it. Let's move on to the fifth question. A spherical metal shell A of radius RA and a solid metal sphere of RB, which is smaller. Okay. This is RB, and let's draw a shell. Okay. RA are kept far apart and each is given charge. Okay, so they are kept far apart. All right. We can just far apart. What that essentially means is that they are not going to influence each other's fields and all that. Neither potential nor fields, right? Now, what it says is they are kept far apart and each is given the charge plus Q by 2. Now they are connected by a thin metal wire plus Q by 2. Okay. They're connected by a thin metal wire. Okay. The switch is basically down there. Then which of the following is or are correct about this situation? Okay, so the first thing that we know is I've already put out a video regarding this, that this is inversely proportional to the local radii. So this is correct just by looking at it. Now, after connections, the charge and so what's happening is that we need to check for the charges, right? We need to check if which has more charges. So what we can do is essentially we can use this result to check for this. Okay, this is of course true, right? So we are going to do this 4 pi r squared, right? This is qa upon 4 pi r a squared. Now we have to compare it with qb and 4 pi r p squared. All right, and the ratio of these two is equals to rb upon ra. That's what that essentially means is this is equals to 1, right? So these are essentially the same. If we can equate them, then what we get is rb. Which one is rb? Okay, this is rb. rb is smaller than ra, right? So when the denominator is smaller, okay, when the denominator is smaller, the numerator has to be smaller with it as well because they are essentially the same. So this value is smaller than this value, then this value has to be smaller than this value. So yes, it is correct. Let me just check the answer for it. Uh, okay, we have still not analyzed the fourth part. Let me just grab the eraser quickly. Okay. So the fourth part says after connections, electric field strength on the surface of A is less than that on the surface of B. RA is larger than RB, and yeah, okay. So what we can do is EA upon EB at the surfaces is equals to QA upon QB multiplied by RB squared upon RA squared. The constants are cancelling out, right? What that leaves us with is going to be RB upon RA, right? Okay, yep. So, yeah, this is also going to be correct. Now let's move on to the sixth question. A particle of mass 2 kgs and charge equals 10 negative 3 coulomb is projected vertically with a velocity 10 meter per second. There is a uniform horizontal electric field of okay. So what's essentially happening is we can calculate the force horizontally. It is going to be QE. So it's essentially going to be 10 newtons. So we have been given with the mass, so we can just divide it by 2 to get the acceleration, which is equals to 5 meter by second squared, right? Now all we got to do is we got to calculate the horizontal range of the particle. We got to calculate the time of flight of the particle, and we got to calculate the maximum height of the particle. Okay. So yeah, the horizontal thing is okay. We just need to check for this. The time is correct. We can get that very easily, and then the maximum height reached would be okay. How do we check for that? We can just use our standard equations that we have been using. So yeah, it's C is also going to be correct. You can just use the standard equations of kinematics, and the horizontal range of the particle is going to be okay. So all we got to calculate is this, and then we have this, and it started from Vx equals 0. So you use Vx equals 0, you use this, and you use time of flight equals to 2 seconds, and you essentially get the result this. Now, do you want me to verify it? I mean, we can verify it. So yeah, that's what essentially happens with us. Now moving on, what do we have with us? Okay. A cubical region of side A has its center at the origin. It encloses 3 fixed point charges, negative q at here, k, yeah, and then another negative q at here. So both of these are essentially forming this line segment. Okay, we just erase this. And then there's 3q at the center. Which of the following options is or are correct? The net flux crossing the plane at x equals okay, so this is the net flux we are talking about. Okay, this is going to be the net flux that we'll talk about. So the net flux of this face is equal to the net flux of the former face, the face backwards, right? So yes, we already know that it is going to be equal. It is going to be q by epsilon naught 6. Okay, yeah. That's the expression for each phase. The electric flux crossing the plane at plus A2. So this is the origin. This is going to be A2. Yeah, this phase we are talking about is more than the net flux. Okay, this is going to be incorrect because both of them are again the same, because the charge enclosed as a whole we are talking about. So this is going to be incorrect. The net electric flux crossing the entire region is given by this expression. Yes, this is true because this cubical region is enclosing a total net charge of Q. So the expression can be given by Q upon epsilon naught. Yes, this is correct. Now let's look for the last option. The net flux crossing the plane at Z. Is this X? I think it is X. Is equal to the net flux crossing the plane at plus A by 2 X. Okay. So it's essentially comparing this phase with this phase, the front phase. So yes, they are going to be equal again. We know that because of the concept of solid angles, and well, we'll just move on then. Alright guys, so the next question that we have with this is, at a distance of 5 centimeter and 10 centimeter from the surface of a uniformly charged sphere, or let's draw a sphere, the potential are, okay, this is 5 centimeters, 0.05 meters away, and this is 0.10 meters away, right? And this is 100 volts, this is 75 volts. We have to check for these statements. So we have to figure out the potential at surface, we have to figure out the electric field at surface, we have to figure out the charge of the sphere, and we have to figure out the electric potential at its center. That's what we have to figure out. Let's get moving. The first step that we can do is we can form equations. So for easing the calculations, I'm taking this plus Rs equals to R, letting that be kq by R equals 100 volts. Then kq by R plus 0.05 equals 75 volts. So from these equations, what we get is 100 volts equals 75 volts plus 3.75. Yeah, I think I might be bad with calculations, so you can just cross check that. 25 volts. So what we essentially get is 3.75 on 25, which is essentially 0.15. Right, that is what we get. Now moving on, this is R, by the way. So the R of surface is going to be 0.10 or 0.1 for simplification's purposes. Now using this we can calculate the potential, the electric field, the charge, and so on. Let's just do that really quickly. So the potential at its surface is going to be what? KQ. We already had the value of KQ. It was, what was it? It was 100 multiplied by R small r, which was 15. 0.15 it turned out to be. So yeah, KQ is 15, and then it is divided by what? So the whole equation is divided by, on both sides it is multiplied by 10. So potential equals 150 volts. Yes, that indeed is correct. Now to get the electric field from the potential, we have this as the potential, we just have to multiply it by 10 again because the radius was 0.1. So this is indeed the electric field. Now calculating for the charge on the sphere. Okay, so the way we can do this is 10 kq equals 150. That is what we had. So kq had equaled 15. Yep. 9 multiplied by 10 to the power positive 9 into Q equals 15. We just do this and this, then we get 5 upon 3 into 10 to the power negative 9 equals Q. Yes, this does in fact satisfy this as well. Now checking the potential at its center. The potential at its center is given by KQ by, what was it given by again? It's given by KQ by R again, I guess, because it is equipotential. The surface is equipotential. So yeah, it's going to be the same, I suppose. Well, either way, this is not correct. Yep. Okay, wait. It was not a metallic sphere. It was not a metallic sphere. So we have to check for its potential due to uniform distribution. Well, what would that be like? We had already memorized the result for a solid sphere which is not metal. So it would be somewhat like 1.5 times the surface, Vs surface. Right, that should give us the electric potential at the center, which was equals to 1.5 into 150, and this gives us 225, which is still incorrect. So yeah, A, B, C are correct. Now moving on to the last question of the day. 6-point charges are kept at the vertices of a regular hexagon of side L and center O, as shown in the figure 1.4 to 5. Given that C equals, okay, so C is a constant first of all. Which of the following statements is or are correct? The electric field at O is 6C along OD. Okay, let's check for that. It's 4. It is 4 times C, I guess. Yeah, it's 4 times C. Then we have, I suppose it is negative, right? Then, okay, wait. I think I did a mistake. So it is going to be 4C this way because it is attracted towards the negative charge. Then it is going to be 2C. So it is going to, and it is going to be 2C again. The angle being the same. These are equilateral triangles, by the way, so we can just write it as 60 degrees and 60 degrees. What that essentially gives us is the sine components of this and this, both of them cancel out. So we just calculate for the cos component. Okay, yes, it is going to be true because cos 60 degrees is 1 by 2. So both of these become 1C and then it becomes 6C in total along OD. A is correct because of the fact that all these charges are going to cancel out each other's potential. They are totally opposite to each other. So yes, this is correct. The potential at all points on the line PR is same. Okay. We just have to calculate the potential at the line PR essentially. So when it is at a distance, so first of all, potential is a scalar quantity. So it does not matter where the direction of or the angle instated on the charges is, what the angle is. We just need to look for the distance from the charge, right? So yes, this is equidistant. Yes, these are equidistant, and yes, these are equidistant, and they will be equidistant throughout this line, and even further beyond they will be equidistant to the perpendicular bisector of ST. So yes, this is true again. Now the potential at all points on the line ST is same. Well, it cannot be the same because when we move on the point extreme point S, what essentially happens is this is lacking behind the potential from this because the radius is quite small here. So I think the correct answers are A, B and C, and that is it for today, guys. Thank you very much for watching.